Okay, thanks. So let's just remind ourselves where we ended off last time. So we discussed duality in monoidal categories, and then we discussed some compatibility between symmetry and duality. So things that hold automatically anytime you have a rigid symmetric monoidal category. So remember, rigid meant that all objects had left and right duals, and symmetric monoidal was this symmetry property that we formalized. And we saw things, for instance, that in any symmetric monoidal category, if you have an object with a left dual, then that left dual is also right dual, right? We saw things like that. And things that the caps and cups, which gave our duality data, slide through crossings, and we saw things like that. And then we started off, but didn't finish, so let me recap. We started off trying to define another one of these universal categories. And it will eventually be called the oriented Brauer category. And I'll summarize the definition at the end, but I want to motivate this definition. So our goal is to define the free, rigid, symmetric monoidal category on a single object. Okay. So remember, we called our generating object up arrow, and we want the category to be rigid. So that means this thing has to have. So we start off by making it a left dual. So we pick some left dual down arrow. And remember, by definition, what it meant for down arrow to be left dual to up arrow is that we have these left caps and cups that satisfy these zigzag relations. Okay, so that's our first step. We now have two generating objects. We have these left caps and cups, and we impose these generating relations. Okay, and then I said there's sort of two ways to proceed now. And the way that we are going to choose is we're now going to focus on forcing the category to be symmetric monoidal. Because we know that if we make it symmetric monoidal, this left dual will automatically be right dual, and then the category will be rigid. Right? So that's the approach that we're going to take. So we want to make it symmetric monoidal. So we know what that means. We need crossings for all of our objects. And it's enough to have crossings for our generating objects, because then we can build crossings for arbitrary objects in the way that's forced on us by the axioms in a symmetric monoidal category. So let's start off with up arrow. We need a crossing that moves an up arrow past an up arrow. So we'll denote this by a crossing where both strands are oriented up. And one of the axioms of a symmetric monoidal category is that this thing should square to the identity. So when we compose it with itself, it's the identity. Okay, so we've added on one more generating morphism and one more relation at this point. Now, in theory, we need all the other crossings. Right? We need this crossing, we need this crossing, and we need this crossing. So you could just plunge ahead and introduce all of these as generating morphisms, and then all the analogs of this double crossing straightening out. But we want to create as efficient a presentation as possible. So it turns out that at least two out of these three we can define from what we already have, and we don't need to introduce them as generating morphisms. So we define our left crossing from the right crossing just by using the left caps and cups to rotate this crossing around, right? And this was suggested to us when we studied the compatibility between symmetry and duality in any rigid symmetric monoidal category. This is always satisfied. And so this justifies this definition, right? But now we're sort of doing things backwards. Instead of knowing that our category is symmetric monoidal and rigid and deducing this, we're trying to make our category symmetric monoidal. And so we're using this as a definition. So we're sort of, in some sense, running some of the proofs we did before backwards. And similarly, we can define the down crossing to take the left crossing and rotate it one more time. Or if you want to go directly from the upward crossing, we take the upward crossing and we rotate both of the legs around. Okay, so now we have a left and a downward crossing. But we need these to satisfy the analog of this relation, that we can pull strands apart with various orientations. Well, one of those comes for free already, so I left this as an exercise. You can take this relation 5.2, and you can attach caps and cups, and you can rotate this relation around, and you can get that the downward crossing already satisfies the relation you need it to satisfy in a symmetric monoidal category. So no more relations at this point yet that we have to add in. And we didn't add in any more generating morphisms either yet, because we just defined these ones this way. But then we reach the point where we have to make a choice. because what we're missing so far is this right crossing. And if you think you can't rotate anymore and get this right crossing using left caps and cups, what you would need is right caps and cups to define it like this from the upward crossing. But we don't have right caps and cups yet. And then, well, we saw before that in any rigid symmetric monoidal category, we could define a right cup in terms of the left cup this way. And similarly, we could define left cap, I think I said cup, left cap in terms of the right cap that way, and similarly for the cups. The problem is here you see that you've got a left crossing, or sorry, a right crossing, and so we have a catch-22, right? We either need to introduce a right crossing as a generating morphism or the right cap and cup, and this is where we make a choice. So we're going to make the choice that we're going to introduce the right crossing. So now we have to add in an extra generating morphism, which is this right crossing. And then we impose these relations that we need this to satisfy to make our category symmetric monoidal. So now we have all flavors of crossing, up, down, left, and right, and they all satisfy this property that if you have two strands, no matter how they're oriented, they pull apart if they're double crossing. So now we can define crossings for arbitrary objects. Because in this category, we have these two generating objects, up and down. And so an arbitrary object is just some tensor product of up and down arrows. And then the crossing for those two objects, we just nest these crossings that we have for left and right, etc. So this is forced on us by the axioms of a symmetric monoidal category. And once we have the crossings for the generating objects, that's enough. Okay, so what's left to make this category symmetric monoidal? We need naturality of the crossings, right? That was one of the axioms of a symmetric monoidal category. So we need that we can take any morphisms and slide them through crossings. In fact, we also need it the other way around, but I briefly mentioned before that once you have this equation on the left that they slide through going from bottom left to top right, you automatically get this one, because you can apply crossings to the top and bottom of this relation, and then straighten out the double crossings, and that gives you this one on the right. So in fact, it's enough to impose this one on the left. And we don't need to impose it for every morphism F in our category. It's enough to have this relation for our generating morphisms, because any other morphism will be built out of the generating morphisms. So once the generating morphisms can slide through crossings, then that's enough. We'll have this naturality. So far, remember, we've got four generating morphisms, right? We've got the left cap and cup, we've got the up crossing and the right crossing. Everything else was built out of these. And we only need to show that it can slide through our two generating objects. So we just need this Y to be either up or down arrow. Okay, so this gives us some relations. We either need to show follow from what we already have, or if not, we need to impose an additional relation. So it turns out for the cups and caps, it follows from what we already have. Okay, so let's see that. So this is what we need, right? This particular relation where F slides through a crossing, if we take our F to be the left cap, then that becomes this relation. The left cap slides through the crossing, right? We saw this a little bit before. Oh, now I've written the same one twice for some reason. Why did I do this?
It's pointing downwards. It's the same.
Oh, yeah, good. It's not the same, right? So here I've moved it past an up arrow. Here I moved it past a down arrow. Thank you. Right. So we need that for the two generating objects. And then if we take the left cup, then it's sliding through the up and the down arrow of these two relations, right? So these are relations we need in order for our category to be symmetric monoidal, and it turns out we can deduce these from what we already have. And essentially, this is, again, running a proof that we saw before backwards. Because before, when we studied compatibility between symmetric monoidal categories and rigid monoidal categories, well, then we have to have this property that the cap and the cup slide through a crossing, and we deduced this cap slide, that crossings slide over caps, right? And we deduce this type of thing. So essentially, we're running this proof backwards now, because now we've defined the left crossing to be this rotated up crossing, right? So now this is our starting point because that's the definition. And then what do? Well, we take that relation. Let me write it over here with more room. So we take this definition of our left crossing, and now we attach a cap, a left cap to this strand. And then you see right here, we've got a zigzag, which we can straighten out using our zigzag relation, this relation 5.1, right, that we imposed. And what we end up with is this cap slide, that crossing slide over caps, okay? And then once we have that relation, we just apply a crossing at the bottom like this. And then we use the, right here, we've got a double crossing of strands and we pull those apart. And that exactly gives this relation, right? So we deduce that the left cap slides through the crossing, and we were essentially running a proof that we saw before backwards. Okay? And the other ones are very similar. So maybe I'll skip the proofs of the other ones. I've written up the details in the notes. People can look at them. But you start from our definition of the down crossing, and then you again rotate it and use the zigzag relation, and then you'll get this second one, right? So they all go like this. Any questions on that? Okay, so let's back up again. What were we trying to do? We're trying to show that all of these generating morphisms slide through a crossing. So for the left cap and cup, that follows from what we already have. We don't need to impose any other relations. We already have that they slide through crossings. So what we're left with now is having to show that for the up crossing and the right crossing. And then our category will be symmetric monoidal. Okay, so that's what we have left to do. F being one of these, the up crossing or the right crossing. Y will be up or down, and we need to show that this crossing slides through. But remember, we thought a little bit about this before. Having a crossing slide through another crossing is just the braid relation. So really what we need to impose, or what we need to either prove or impose, is the braid relation for various orientations of the strands in the braid relation. Okay, so we can't deduce any of these from what we have so far. So we need to impose at least one of them. So let's impose this one, the braid relation for all the strands oriented up. So that's the case where F is the up crossing and Y is up arrow. So that's the up crossing sliding through an upward oriented strand. Okay, so we impose this relation. This is going to be one of the relations we impose in our category. And it turns out that that's enough to deduce all of the other cases. We don't need to impose any other relations. So let's see how that works. What are the other cases we would need? In a priori, for this braid relation, there are 8 ways to orient these 3 strands, right? But we don't need to prove all of those versions of the braid relation because we only need up crossing and right crossing to pass through. So what we need in addition to the one we just imposed is these 3. So you see this first one is, what is that? That's the right crossing sliding through an upward strand. This one is the upward crossing sliding through a downward strand. And this is the rightward crossing sliding through a downward strand, right? So those are the 3 versions of the braid relation that we really need to prove. And the idea, so I'll go through maybe the details of the first and the second, and then the third I've written up, but I won't discuss here because it's similar. But the idea is that we take this one that we imposed, and we use cups and caps to start rotating this relation around, and maybe apply some crossings to top and bottom to move the strands around. That's the general idea. Okay, so let's see how this works in detail. Okay, so let's focus on this first one we want to prove. Okay, so we start off with our upward oriented braid relation, the one that we imposed. Let me give myself lots of room here. Okay, so we start off with that relation. And now what we do is we take this strand, we attach a left cap to bend it down. And we take this strand on the bottom and we bend it up with the right cap. Okay, so then we get exactly this picture that I drew here. So far we've just rotated that upward braid relation around. Then what we do is the following, just a little slight trick. Right in here and right in here, I'm going to insert a zigzag. So let me try and draw that. So we're going to have this, and now I'm just going to insert a zigzag here, like that. And same thing on the other side. So I've got this, and now I want to insert a zigzag. And the reason I do that is now, if you look right here, I've got a rotated upward crossing. I've got an upward crossing that I've rotated with the right cap and cut. So that's exactly the left crossing right here. And then right here, again, I've got this rotated crossing. So that exactly becomes the left crossing up here. Right? So we've just rotated this relation around. So what we end up getting is another version of the braid relation, but the strands are in another orientation. So we just started with our one that we imposed and we rotated it. But it's not yet any of these three that we need. It's just one of the other 8 that actually we don't need, but we use it to deduce one of these 3. So the last step is that we take this one we just proved and we cross the top 2 strands on the right and the bottom 2 strands on the left. Right? And then right here, we've got a double crossing, and right here, we've got a double crossing. And if you pull those double crossings apart, okay, so first of all, I wrote what you get right here when you put those crossings on the top and bottom, so this is a bit easier to see. Here's that double crossing, and here's a double crossing. And now we just pull those double crossings apart, and it gives exactly this relation on the left. Okay, so we first rotated, and then we used crossings to move one of the strands over. And that's the idea. So you play around and you can get any version of the braid relation you want in this way by these caps and cups and crossing strands. So let's do maybe one more, this one. We take the equality that we actually just proved. So let me write it here. So the one that we just proved is sometimes called the alternating braid relation, because the orientation of the strands alternates as you go around. And now we compose on this top with a crossing here and on the bottom here. And then again, you pull apart these strands that double cross and you look at it for a minute and you convince yourself that that gives you this one. Okay. And then the very last one that we need, this one, is very similar. So I've written up the details in the notes, but it's the same idea, right? So hopefully people will get the flavor. We only had to impose this one version of the braid relation, and then we can rotate and use double crossings to get all the other versions. Any questions?
Yeah, is there a way a priori that you could have seen you only need to impose one, or do you have to do the calculation to see it once and
I think you need to do the calculation because you need to be a little bit careful, because at this point we only have left caps and cups. So you can only rotate things to the left and then move things past to the right. So you got to be a little bit careful. If you had both right caps and cups, then I think you could convince yourself pretty easily you could get all of them, because you can just rotate any way you want to move them around. You have to be a little bit careful that you're only rotating to the left.
Put in more generators.
You get a different presentation, which I will mention. So that was that other approach, right? So the rows diverged at one point, where you could have added in the right caps and cups instead of the right cross. You get a different presentation of the category, and I'll give that presentation too. Yeah, and then then you have to deduce the other properties, and so you give slightly different proofs, but they're all sort of the same flavor. Any other questions?
So in the end, is it true that these morphisms are determined up to?
are unique once you specify the endpoints and the orientations.
That's right. So, yeah, I'll mention this when I draw pictures. So what it ends up being is just like crossingless. No, sorry, match. Yeah, it ends up being what they call it, a perfect pairing of endpoints, basically where orientations match. That's right. Plus some bubbles, unless you specialize these bubbles. That's exactly right.
Could we have added in a different break relation and rotated it to get this way? Or was it important that we added this one? And did you get this one?
No, you probably could have started with some other ones. I think, for instance, if you took this one and rotated it to the right, you could start with that one because we're allowed to rotate to the left. I'd be a little bit worried maybe if you took this one and rotated it left and started with that one, you wouldn't be able to get this one because we can't rotate to the right. So I sort of started with one that was maximally on the right, and we could rotate to the left. Yes?
How does one go about showing that you can't get any break relation with the prior data?
That's a good question. I mean, I made this statement that it doesn't follow. I mean, I guess in theory, the way you could prove this is you could take the relations we have so far, and if you can find a functor to some category that doesn't satisfy this relation, then that would be enough. But I can't off the top of my head think of such a category, but that's how you could try to prove something like that. Because, you know, in theory, this is sort of a hard thing to prove that some relation doesn't follow from other relations. But that would be the strategy I would try. Other questions? Okay, so now we have a symmetric monoidal category because all our generating morphisms slide through all the strands, the upward and downward oriented strand. And now we can, now we can define a right cap in terms of the left cap because we have a right crossing, and we can define a right cup as well. And then we saw before when we were discussing the compatibility between duality and symmetry, that it follows automatically that you have these right zigzag relations. We went through that proof. So now this down arrow is both left and right dual to up arrow, right? Because that holds in any symmetric monoidal category, and now we've made it symmetric monoidal. Okay, so now I'm going to summarize what we did. So this is the definition of the oriented Brauer category. So you fix some ground field K, and it's the strict monoidal. I should add in K linear. Category generated by up arrow and down arrow. The morphisms we had to add in were the up crossing and the right crossing, the left cap and the left cup. And the relations we had to pose were that strands pull apart in this way. We did not need to impose the one that the downward oriented strands pull apart. That followed from these ones. We needed to impose this one version of the braid relation and the left zigzag relations. And that's it. Everything else followed from those ones. Now, if you look in, in these two relations, they involve a left crossing. So when you give the presentation without any of the background motivation, you need to specify that that left crossing is how we defined it, the rotated up crossing. Okay? Otherwise, those two relations that I highlighted there don't make any sense. So that's the oriented Brauer category. Now, we often want to do one more thing. We take some element of our field and we impose the condition that this figure 8 is D times the identity morphism of the unit object. And why the figure 8? Again, I'm just drawing it as a figure 8 because I want to write it in terms of our generating morphisms. But remember, if we define our right cap to be this twisted left cap, then that just becomes that the bubble is D times the identity. And remember, we had an interpretation for that. That's the categorical dimension of this up arrow. So the relation that we're imposing is that this generating morphism has categorical dimension D. And I call this the specialized oriented Brauer category. But in the literature, if you look up oriented Brauer category, it may just include this relation. Okay, so you have to just be careful about whether they're including that relation or not. Okay, so that summarizes what we did so far. Any questions on this definition?
How do we know that specializing D doesn't cause us into collapse?
That's a good question. So a priori, that would be hard. The way you can prove that is that we'll define a functor to a category that's not the zero category. So we'll define a functor to the category modules over the general linear group, and therefore you know it doesn't collapse. But in general, you have to be worried about that type of thing. Sometimes you can impose too many relations and your whole category collapses to zero category. Other questions? Okay, so it follows from our discussion, the way that we motivated this, that this oriented Brauer category is the free, rigid, symmetric monoidal category on one object. And if you impose this extra relation on the categorical dimension, then it's the free, rigid, symmetric monoidal category on an object of dimension D, categorical dimension D. So these have the corresponding universal properties, which I won't write down. We've written down a few of these before, and we'll use this universal property in a minute. And if you haven't seen these before, let me draw an example of what these morphisms can look like. So the objects are just finite tensor products of up and down arrow. And then a morphism is a linear combination of what are called oriented Brauer diagrams, which is your domain is given, the up arrows and down arrows that appear are the factors of your domain object, prescribe the orientation of the strands at the bottom, and then the strands at the top, their orientation is determined by your codomain. And then you can pick any string diagram that connects the bottom endpoints to the top endpoints so that the orientations match, and you can have cups and caps and they can cross each other, right? And as Andrew pointed out, this is what he was getting at, that it really only depends on which endpoints are connected, because our relations allow us to isotope from one to any other one. And you can take any linear combinations of these types of diagrams. So this was in the specialized Brauer category. If I don't impose this extra condition that the bubble is D, then you can also have some floating bubbles around. You can show that the two orientations of the bubble are equal, right? So there's just really one bubble that floats around, but if you don't add in the specialization, then your diagrams can have these bubbles floating around as well. Okay, so any questions on that?
So if you have bubbles, doesn't matter where they are.
It does not, because of the axioms of symmetric monoidal category, the strands slide through other strands, so you can slide the bubbles anywhere you want, so they're just floating around. All that matters is you have a sort of a polynomial in the bubbles sitting there at the side.
The morphism of without specializing, any morphism up to unit objects, polynomials, and bubble.
That's right, exactly. It's exactly polynomials in the bubble. And then you're sort of doing a base ring extension, or you're collapsing by evaluating the bubble when you go to the specialized Brauer category. Okay, so let me give the alternative definition. Remember, there was this branching point in our approach where we had to decide, are we going to add in the right crossing or are we going to add in the right cap and cup? So if you repeat this exercise that we did to motivate the definition, but at that critical point, you take the other path, which is you add in the right cap and cup, then this is the definition that you would come to. So now we've got an up crossing, the left and right caps and cups, but we don't have to add in the right crossing now. And we have to impose these relations that the upward strands pull apart. We have the upward braid relation. The up and down strands pull apart in that way. We need these curl relations. And so the reason we need these curl relations is because in the other approach, we defined this to be this. And if you rotate this picture, that's the curl relation. But in this other approach, we have independently a right and a left cap and cup. And so this is some compatibility between the two that we now have to put in as a relation. Whereas before it was essentially a definition. And then we need the left zigzag relations. And so in this approach, the left and the right crossings are both determined in terms of the other, or defined in terms of the other generating morphisms, because now we can rotate both left and right. You'd also have a downward crossing, but it doesn't appear in any of the relations. So we didn't write that. And then your specialized one, now you can just write it as a bubble. You don't need the figure eight because you have right and left caps and cups.
Well,
what's the relation between this and the modify BT thing?
Yeah, that's a good question. The difference is instead of this crossing in the hum flip skein category, you have over and under crossings. And then the relations that they would satisfy. So, you know, you'd have to change this relation to this relation. They only pull apart if they're composed in the right way. And then, you know, this, I might get the power right, it's either T or T inverse times this. You've got some other parameter for this curl. So if you take the hom flip skein category and you specialize the parameters that sort of collapse these categories to this, or these crossings to the same thing, then it becomes this oriented Brauer category.
The
So,
other row is identity.
pardon me?
The other row is identity.
No, both of them, again, I have to sit down and make sure I get it right. Yeah, it's either this one or the other one where it passes over instead of under. It would also be T inverse. It's the other one, yeah. Just sit down and play with the pictures a second. And then if I flip the crossings, it's a T instead of a T inverse. In fact, I don't know why I wrote T inverse. I got it written T. It just depends on the way you choose your parameter. And then you've got another parameter, which is that over crossing minus under crossing. So is Z times the identity. Sometimes that Z is written as Q minus Q inverse. So if you take Z to be 0 or Q to be 1, these crossings, then these crossings become equal, right? And then you take T equal 1 so that these become that curl relation, and then it collapses to the oriented Brauer category. Other questions? Yeah, you're right. The orientations are wrong. This one should be oriented up, and this one should be oriented down. I think I caught that in that first definition, but I forgot to catch it here. Is that what you meant?
Yeah.
Yeah, that's right. Thank you. Let me do this, so I'll change it in the notes after. Any other questions? I think that'd be pretty trivial because you're not distinguishing between over and under crossings. So everything just becomes, any knot just becomes some collection of bubbles. It'd just be counting connected components, basically. Okay, so what are the applications of this? I mean, I think this is sort of a neat thing in general that you can create these universal categories, but the reason really we want to do this is to use them to study representation theory, because there are various categories of modules that we know have these duality and symmetry properties. And so therefore, we automatically have a functor from these universal categories into those module categories. And then we want to use all the things that we learned about those universal categories to study the representation theory. Okay, so our application for this oriented Brauer category is going to be to the general linear group. So we'll take the general linear group, field K, and V will just be the natural module. So just d-dimensional space with action given by matrix multiplication. So this is a category that has duals, right? There's a dual module. Any module for a group has a dual module. And it has, this is a symmetric monoidal category. The category of modules over the general linear group is symmetric monoidal with the symmetry just given by the flip. So it has these properties, and therefore, by the universal property of the oriented Brauer category, we have a functor from the oriented Brauer category to the category of finite dimensional modules over the general linear group that sends our generating object up arrow to this natural module and sends down arrow to the dual of the natural module. And so it sends the crossing to the symmetry data in the module category, which is flip, just the usual tensor flip. We have to say where it sends the right crossing, that's also flip, but now you're flipping V and V star. It's just the usual flip map on a tensor product. And we saw this before when we did example of duals. The left cap is sent to this evaluation map, and the left cup is sent to the co-evaluation map, right? So we saw those before. And that's all I need to do to specify it, because those are the generating morphisms. I don't need to tell you what it does on the right cap and cup or any of the other crossings, because it's uniquely determined by these ones. That's one of the things we gain out of this approach of having a minimal presentation, is that to define the functor, we reduce the amount of work that we need. We just need to define it from these things. And in fact, you can save yourself even a little bit more effort, that in fact, you only need these first three. You need to specify those because there was an exercise way back, if you remember, was about how unique this duality data is. And I said it's not unique in general, but if you fix one of them, like if you fix the cap, then the cup is uniquely determined. So if we say where the cap is sent, the fact that the target category is rigid monoidal means there exists a unique image for the cup. And so you really only need to specify where you send those first three. So now as an exercise, you can see where things like the down crossing, the left crossing, and the right cap and cup are sent, because they're defined in terms of the other things, right? So remember, left crossing was this, so that involves an up crossing and a left cap and cup, and I've told you where those get mapped to, and so you can just compute where the left crossing gets sent to, and it's what you guess it would be. It's the flip of V dual, right? And same thing for the other ones. So the right cap and cup, for instance, are evaluation and co-evaluation for V star, as long as you identify V double dual with V in the usual way, so that these have a V appear here instead of a V double dual for these evaluation maps on the dual. Okay, any questions here? Okay, so a little exercise that's, if you haven't done these types of things, is useful. We just said by the universal property there exists this functor. You can also just check directly the defining relations of the oriented Brauer category, right? And they're not so hard, so you can just compute them all directly and see that this functor is well defined. Okay, but here's the key result. So we have this functor, but that functor isn't that useful unless it captures all of the information in the target category. So what are the objects that are in the image of this functor? They're all tensor powers of the tensor products of the natural module and its dual. And then we have morphisms, homomorphisms between those tensor products. And what we really would like is that our functor is full, so surjective on morphism spaces, so that all homomorphisms between all of these tensor products of V and V dual are in the image. And so we can really study them all by studying the oriented Brauer category. And that turns out to be true, as long as we make some assumptions on the ground field. So the ground field has to be infinite. So for instance, over complex numbers, it's the idea of this proof, because it uses, in the end, it comes down to Schur-Weyl duality, or part of the statement of Schur-Weyl duality. But there are these sort of standard tricks one uses to reduce it to the statement, or half of the statement of Schur-Weyl duality. So I want to emphasize these techniques, because it's standard, it appears over and over again in this type of thing. So what we really need to show is that for any two objects in the oriented Brauer category, the map between Hom spaces that's induced by this functor is surjective, right? That's what it means to be full. So that's what we need to show. Okay, so let's take two arbitrary objects, so X and Y. So what arbitrary objects in this category are tensor products of up and down arrows. So let's just say X has Rx copies of up arrow, and Y has Ry copies of up arrow, and X has Sx copies of down arrow, and Y has Sy copies of down arrow. Right, so I've just given a label to the number of times that up and down appears in X, Y. Okay, so now this is the thing we want to show is full, this functor here. The idea is we're going to have this commutative diagram and reduce it to showing that this thing at the bottom is surjective. And that will follow from Schur-Weyl duality. So how do we get this commutative diagram and turn the statement that the top one is surjective into the equivalent statement that the bottom one is surjective? Well, we do this in two pieces. The first idea is that in X and Y, in X, we want to move all the up arrows to the right and all the down arrows, up arrows to the left and down arrows to the right. And in Y, we want to do the opposite thing. We want to move all the down arrows to the left and all the up arrows to the right. And the way that we can do that is because up tensor down is isomorphic to down tensor up, with the isomorphism given by the crossing. So what we do is so this box is some arbitrary diagram, and anytime we see an up arrow to the right of a down arrow, we attach a crossing at the top. And we keep doing this to move all the up arrows to the left and all the down arrows to the right, right? And these are isomorphisms. This is invertible because we could pop the other crossing on the top and move it back, right? And then on the bottom, we do the other thing. We want to move all the down arrows to the left and all the up arrows to the right. So what we end up getting this isomorphism between this Hom space between arbitrary objects to one where in the domain, all the down arrows are on the left and the up arrows are on the right. And in the codomain, all the up arrows are to the left and the down arrows are to the right. Okay. And we can do the exact same thing on the GL mod side. We just take the image of these crossings, which is the flip, right? So we pre-compose and post-compose with this flip to move all occurrences of V star to the left and V to the right in the domain. And in the codomain, we move all occurrences of V to the left and V star to the right. Okay, so we're just using the symmetry in our category. So now we've got it to showing that this functor in the middle, or this map, is surjective. And now one more step, and that's best illustrated by this picture. So now we've got something like this, some arbitrary picture in this box. And in this picture, look, you see that in the bottom, which is the domain, all of the down arrows are to the left of all of the up arrows, right? So that's what we did in our first step. And at the top, which is the codomain, all the up arrows are to the right of all the down arrows. So this is the type of picture we have now. But now we apply this map, and we saw this idea in Ben's talk, for instance. We can now use our caps and cups to bend all these down arrows in the bottom and turn them into up arrows on the top. And similarly, we can take all these down arrows on the top and bend them around so that they become up arrows on the bottom. Right? So that is a map. That's this isomorphism. Oops. This isomorphism is that bending around. And that's an isomorphism because it has an inverse, which I just drew here, right? Because you can bend them back. And these maps are mutually inverse because of our zigzag identity. So if you bend these up and then you bend them back down, you get back to what you started because you can pull zigzags straight. Okay. So what this tells us is now we've reduced our situation where everything is up. Right, so you see that here we only have tensor powers of up arrow appear anywhere, and here we only have V's. There are no V duals because we brought all V duals to the other side, right, using our duality. Okay, so now we're reduced to this situation, right? So now we only have to look at Hom spaces between various tensor powers of up arrows and where that goes, which is homomorphisms between tensor powers of this natural representation. There are no more down arrows, no more duals, because we use these tricks to get rid of them. So that's the key step that occurs again and again in this type of proof that I wanted to emphasize. So before we continue, any questions on that?
I have a comment.
Yes.
It's a sort of reverse proof that the Wald-Brauer algebra occurs. I mean, the short algebra in that case.
Right.
From classical.
That's exactly right. Yeah. You're moving duals from top to bottom, etc. Yeah, it's the same idea. So you see this idea comes up again and again.
Yeah.
Okay, so now we want to reduce to that. So there are essentially two cases. We want the case where R is not equal to S and where R is equal to S. So when R is equal to S, I claim that actually both of these Hom spaces are 0. The diagrammatic side is not hard to see. You can't draw any diagrams joining R up arrows at the bottom to S up arrows at the top if R is not equal to S, because you can't create up arrows. There's no morphism that does that. But to show it's surjective, what's more important is that the right-hand side is 0. So the way you can see the right-hand side is 0, for instance, if you take any non-zero element of your field, and you look at that multiple of the identity matrix, that's central, right? So it commutes with the action of GLD. And so any homomorphism between two objects where that central element acts in a different way, that has to be 0, right? But it acts on V tensor R as alpha to the R. So if R is not equal to S, then you can't have any non-zero homomorphisms because it wouldn't commute with the action of this element, because on the domain, it would act by alpha to the R, and the codomain, it acts by alpha to the S. So it doesn't commute with this action. Right? So when R is not equal to S, this target Hom space is 0, the map is surjective automatically. It happens to be an isomorphism because the domain is also 0.
Just where the infinite size of the field.
Well, maybe if your field is really small, like if it's a field with 2 elements, so your only choice for alpha is 0 or 1, this might break down. But this would even work for some finite fields, this part of the argument type. Oh, no, maybe not. No, you're right, yeah.
For any finite field, this should be like a Hom plane.
Right.
B tensor R, B tensor S to speed.
Right, because you could just take this, yeah, if you take this power R so that alpha is equal to alpha to the R, then this argument breaks down.
Could use another great field maps.
The assumption that the field is infinite. Or
Yes, that's right, now, sorry,
So should be there would be these here.
should there be what? Oh, those should be these, yeah. Change that after, right? Okay, so now we're left to the interesting case, which is when R is equal to S. Again, I just realized there's a mistake here. What I want here is endomorphisms in the oriented Brauer category of tensor R. Okay, so when you have R up-pointing strands, you've got an algebra homomorphism from the group algebra of the symmetric group into the endomorphism algebra in the oriented Brauer category that sends a simple transposition SI to crossing of the I and I plus first strings. We saw a similar thing in the very first lecture when we introduced this universal symmetric monoidal category that just had crossings. We had a similar map. So that one sits inside this oriented Brauer category. It's just pictures where you don't have caps and cups. So we have this map, and then if you compose this with our functor, now to end GL DK V tensor R, this is the standard map from the group algebra of the symmetric group to this endomorphism algebra that just swaps factors, right? And the fact that this is surjective is precisely Schur-Val duality, right? So we've reduced it to Schur-Val duality. So that's the general trick that occurs again and again. There's often this fact that was known way before people started considering the monoidal categories. People knew this way a long time ago. And then you have this sort of enhanced monoidal category version where you say that a functor is full, but really it ends up coming down at the end to the same statement that people knew before. They were looking at it from the point of view of monoidal categories. Any questions? Okay, so that's a good place to stop. I'm out of time. Well, let me just say this remark. When D is big enough, this map is also injective instead of just surjective on morphism spaces. The endomorphism algebra is sometimes called the Wald-Brauer algebra when all your ups are to the left of all your downs, and that's because all your caps and cups have to go one way. So you have an imaginary wall here that they're crossing. So this is the Wald-Brauer algebra. And you can give explicit bases for these morphism spaces, so you can get very concrete. And these are also related to Deline's interpolating categories. People have seen those. You have to do something like something called take the idempotent completion and then the semi-simplification, then you get to Lean's interpolated categories. Okay, so I'll